As described, when testing a null hypothesis versus an alternative hypothesis, a decision threshold, called the level of significance, is denoted by the Greek letter alpha, which is a pre-specified value such that if the p-value is less than or equal to alpha, the null hypothesis is rejected, and we conclude that our data provide evidence in support of the alternative hypothesis. Otherwise, we fail to reject the null hypothesis. We consider that there is some underlying truth such that in reality, either the null hypothesis is true or the alternative hypothesis is true. Unfortunately, we do not know the truth, but use our collected data to make a decision about which is true. Once we have made a decision, there are two errors that we could have made. A type 1 error is when we reject the null hypothesis when in fact it is true. A type 2 error is when we fail to reject the null hypothesis when in fact it is false. We are interested in controlling the probabilities associated with making these types of errors. In this table, the columns represent the underlying truth, which is unknown to us, and the rows reflect our decision after performing our hypothesis test using our data. Of course, we could have made a correct decision. However, we see that if the null hypothesis is in reality true, yet our inferential test led us to reject the null, we commit a type 1 error. We also see that if the null hypothesis is in reality false, yet our inferential test led us to fail to reject the null hypothesis, then we commit a type 2 error. Typically, we control the probability of committing a type 1 error by fixing alpha. In the microarray setting, there are often thousands of genes, each measured on a quantitative scale, and it may be desired to determine what genes are significant or important. Suppose there are G genes and you perform a two-sample t-test for all G genes. You may be inclined to provide your collaborator with a list of genes where the genes are ordered by p-value. This is not a good idea because your collaborator will likely look through the full list until they find a gene name that they are familiar with. Given the large number of tests applied, they may be likely to commit a type 1 error. That is, when many hypotheses are tested, each at a specified type 1 error probability, the probability that at least one type error is committed increases sharply with the number of hypotheses tested. In fact, when testing 10,000 genes, each at the alpha equals 0.05 level, we would expect 500 genes to be identified as significant just by chance alone. To solidify this concept, feel free to execute this example code in R. In the first line, we create a data matrix that will have 10,000 rows representing genes and 16 columns representing samples. We generate levels for a factor variable to represent group, where there are 8 observations in each of 2 groups. I set the random seed only if you want to replicate my results. Then for J going from 1 to 10,000, the data matrix is filled in by drawing a random sample of size 16 from a standard normal distribution. Note that all 16 observations are drawn from the same distribution, so there is no difference between either group of 8 observations. After the data matrix is filled in, then for each row, a two-sample t-test is performed to compare group 1 to group 2, and the p-value is extracted and saved. The p-value vector then is of length 10,000. When summing how many rows have a p-value less than 0.05, there are 480 in this example. This is very close to the expected 500. This exercise highlights that although the two-sample t-test or Wilcoxon rank sum test may be employed for testing each null hypothesis, it is important to make appropriate adjustments for multiple comparisons. When testing G null hypotheses simultaneously, the family-wise error rate is the probability of at least one type 1 error in the family. We can control the family-wise error rate either weakly, when all null hypotheses are true, or strongly, which is under any combination of true and false null hypotheses. We will be using the notation here that G genes will be tested, and we will index genes using the letter J. Letting P equal the probability of committing an error, that means 1 minus P represents the probability of being correct. If the G hypothesis tests are independent, the probability that there is at least one error among the G hypothesis tests is given by this equation. Note that this equals 0.994, so that this probability is 1 for virtually all high-throughput genomic experiments, because practically all assays interrogate more than 100 genes. The first method to control the family-wise error rate is the Sidak single-step method. When testing G null hypotheses, reject any null hypothesis having a p-value less than this value. Suppose we are analyzing data from an assay that includes 1,490 genes. Using this method, we would compare all resulting p-values to this threshold. The simplest approach to correcting for multiple comparisons is to simply divide the desired type 1 error rate alpha by the number of comparisons being tested, which is G. This is the Bonferroni procedure and is likely the most well-known method for adjusting for multiple comparisons. The Bonferroni method is therefore similar to the Sidak single-step method, as each test is compared to one single threshold. Suppose we are analyzing data from an assay that includes 1,490 genes. Using this method, we would compare all resulting p-values to this threshold. Both of these single-step methods decrease power as the number of hypothesis tests increase. That is, the single-step methods may lead to a failure to accept a truly significant different test result. Both are very conservative and do not attempt to incorporate dependence between tests. The Holm step-down procedure recognizes that once a test has been performed, there are then G-1 tests remaining. Therefore, this procedure attempts to incorporate some dependence between tests. The procedure begins by first ordering the p-values from largest to smallest. Here, the parentheses in the subscript denotes the ordered statistics. Then, starting with J equals 1, compare the Gth p-value, that is, the smallest p-value, to alpha divided by G. Note that this is the Bonferroni method. If the smallest p-value exceeds this threshold, fail to reject all hypotheses. If the smallest p-value is less than or equal to this threshold, reject the null hypothesis and increment J. Then return to step 3. Now you will be comparing the second smallest p-value to alpha divided by G-1. If this p-value exceeds the new threshold, fail to reject all hypotheses. If this p-value is less than or equal to the new threshold, reject that null hypothesis and increment J. Repeat until you stop or reject all hypotheses. The Sidak step-down procedure is similar to the Holm step-down procedure, with the exception that the threshold is based on changing the Sidak threshold rather than a changing Bonferroni threshold. Hochberg step-up starts by ordering the p-values from largest to smallest, then compares the largest p-value, which is when J equals 1, to alpha divided by J, which, when J equals 1, is simply alpha. If this p-value is less than or equal to this threshold, reject all remaining null hypotheses. If the p-value is greater than this threshold, fail to reject this null hypothesis, increment J, and return to step 3 and repeat the procedure. For our example, where we may be interested in testing 1,490 genes, the different thresholds for these family-wise error rate control methods are provided. As you can see, the values are quite small given the large number of features, so there isn't much difference between them. Controlling the family-wise error rate is practical when very few features are expected to be truly different, for example, in genome-wide association studies, or GWAS, because any false positive can lead to a large waste of time when conducting confirmatory studies. However, it can be too conservative because guarding against any single false positive occurring is often going to be too strict and will likely lead to too many missed findings. The table on the previous slide can be produced using this R code, where G is the number of tests and alpha is the significance level. Alternatively, the p-adjust function in R can be used. The adjusted p-value corresponding to the hypothesis can be defined as the level of the entire test procedure at which the null hypothesis would be rejected, given the values of all test statistics involved.